Welcome back to the session on numerical integration. In this session, we shall discuss the Simpson's rule of numerical integration. We have the Newton's Cotes formula, integral from x naught to x n y dx is equal to h into n y naught plus n square by 2 into delta y naught plus 1 by 2 into n cube by 3 minus n square by 2 into delta square y naught plus etc. This is a general formula known as Newton's Cotes formula. In this formula, we put n is equal to 2 and assume that there are only 3 paired values of x and y, or assume that the interpolating polynomial is a second degree polynomial. We get integral from x naught to x2 y dx is equal to h into 2 y naught plus here 2 square by 2 is 4 by 2, that is 2 times delta y naught plus 1 by 2 into n is 2, therefore n cube is 2 cube, that is 8 by 3 minus 2, here 4 by 2 is 2, that is 1 by 2 into 8 by 3 minus 2 into delta square y naught. The remaining terms are does not exist because we are given only 3 paired values of x and y. This is equal to h into 2 y naught plus 2 times delta y naught is delta means the forward difference operator, therefore delta y naught is y1 minus y naught. Therefore this term 2 into delta y naught become 2 into y1 minus y naught plus 1 by 2 into here 8 by 3 minus 2 into 1 by 2, that is 1 by 3 into delta square y naught. Delta square y naught means delta is e minus 1 where e is the shift operator, e minus 1 square y naught, that is equal to on expansion we get y2 minus 2 y1 plus y naught. Therefore, we substitute the value of delta y square here, we get this term will become 1 by 3 into y2 minus 2 y1 plus y naught. This is equal to h by 3 into, on simplification we get h by 3 into y naught plus 4 y1 plus y2. This is known as Simpson's 1/3 rule, that is integral from x naught to x2 y dx is equal to h by 3 times y naught plus 4 y1 plus y2. Now, let us discuss the composite Simpson's 1/3 rule, that is integral from x naught to x2n, that is we divided the whole length into 2n equal subintervals. We get integral from x naught to x2n y dx is equal to integral from x naught to x naught plus, here we can write x2n as x naught plus 2nh y dx, which is equal to integral from x naught to x2 y dx plus integral from x2 to x4 y dx plus etc. plus integral from x2n minus 1 to x2n y dx is equal to, this is equal to, value of this integral is h by 3 into y naught plus 4y1 plus y2. We just derived the value of this integral as h by 3 into y naught plus 4 times y1 plus y2. Similarly, value of this integral will become h by 3 into y2 plus 4 y3 plus y4 plus next integral is h by 3 into y4 plus 4 y5 plus y6 plus etc. plus h by 3 into the last integral is y2n minus 2 h by 3 into y2n minus 2 plus 4 times y2n minus 1 plus y2n. This is equal to h by 3 into, h by 3 is common, into here y naught, here 4 y1 plus 4 y3 plus 4 y5 etc. Therefore, we can combine the terms. Y naught is only 1, also y2n is only 1. Therefore, we can write y naught plus y2n plus 4 times here y1, in this case y3, here y5 plus etc. plus here y2n minus 1 plus y2 is here and in this term also y2 contained. Therefore, 2 times y2. Similarly, 2 times y4 etc. Therefore, plus 2 into y2 plus y4 plus etc. plus y2n minus 2. That is integral from x naught to x2n y dx is equal to this. This formula is known as the composite Simpson's 1/3 rule. The geometric significance of this rule is that we replace the graph of the given function y equal to f of x in the interval x naught x2n by n arcs of second degree parabolas with vertical axis. Note that to apply this composite Simpson's rule, the interval of integration must be divided into an even number of subintervals, each of the same width h. Now, Simpson's 3/8 rule. In this Newton's cotes formula, we substitute n is equal to 3. We put n is equal to 3 and omitting the terms with the delta raised to 4 y naught and higher order differences in the interpolating polynomial, we get integral from x naught to x3 y dx is equal to h into 3 y naught plus 9 by 2 into delta y naught plus 1 by 2 into 9 minus 9 by 2 into delta square y naught plus the next term is 1 by 6 into 81 by 4 minus 27 plus 9 into delta cube y naught, which is equal to h into 3 y naught plus 9 by 2 into delta y naught is y1 minus y naught. Delta is the forward difference operator, therefore, delta y naught is y1 minus y naught plus, on simplification we get this as 9 by 4 into delta square y naught is y2 minus 2 y1 plus y naught. Delta square y naught means the second forward difference, this plus 1 by 6 into on simplification we will get this quantity as 3 by 8. Delta cube y naught is y3 minus 3 y2 plus 3 y1 minus y naught. That is the third order forward difference operator. Therefore, delta cube y naught is y3 minus 3 y2 plus 3 y1 minus y naught. This is the Simpson's 3/8 rule of integration. Now, let us see the composite Simpson's 3/8 rule. That is, we divide the total interval into 3n equal subintervals. We get integral x0 to x3n y dx is equal to integral from x0 to x3n can be written as x0 plus 3 nh y dx, which is equal to integral from x0 to x3 y dx plus integral from x3 to xx y dx plus etc. in general plus integral from x3n minus 3 to x3n y dx, which is equal to value of this integral, that is integral from x0 to x3 y dx is here this. On simplification we get this as 3h by 8 into y0 plus 3 y1 plus 3 y2 plus y3, value of integral x0 to x3 y dx is this, that is this is obtained from this expression on simplification, plus similarly value of this integral is 3h by 8 into y3 plus 3 y4 plus 3 y5 plus y6 plus etc. plus value of the integral from x3n minus 3 to x3n y dx is y3n minus 3 3h by 8 into y3n minus 3 plus 3 times y3n minus 2 plus 3 times y 3n minus 1 plus y 3n. This is equal to 3h by 8 is common. Therefore, this is equal to 3h by 8 into here y naught is only 1 and y 3n, last term is y 3n. Therefore, we can write y naught plus y 3n plus 3 times y 1, 3 times y 4, etc. 3 times y 3n minus 2, that is 3 times y 2, sorry, 3 times y 1, here y 4, in the next term it is y 7 plus etc. plus 3 times here y 2, y 5, etc. Next is y 8 plus etc. plus 2 times here y 3, here also y 3. Similarly, we get 2 times y 3 plus y 6 plus y 9 plus etc. Three h by 8 is common, therefore we use the bracket. This formula, that is integral from x naught to x 3n y dx equal to this, is known as the composite Simpson's 3/8 rule. Simpson's 3/8 rule. To apply this rule, the interval of integration must be divided into a 3 multiple number of subintervals, each of the same width h. Now, let us see the geometrical interpretation of the Simpson's rule. Let DC be the curve of the equation y equal to f of x. Now, we draw the perpendiculars DA and CB. Just to draw the perpendiculars D and CB to the x axis and divide this length AB into even number equal parts of the same width by means of the points x1, x2, etc., x2n plus 1. Through these points of subdivision, the points are x1, x2, etc., x2n plus 1. Through these points of division, we draw the ordinates y1, y2, etc., y2n plus 1. Now, the parabola passing through the points D, here we denote P1, here P2. The parabola passing through these 3 points D, P1, D, P1 and P2 is a close approximation to this curve like this. This is a parabola. We replace the arc D P1 P2, D P1 P2. of the curve y equal to f of x by an arc of this parabola whose axis is parallel to the y axis. Hence, the area d A2 P2. Here we use the point A2, here A1. The area of this portion dA A2 P2 D. is approximately equal to the area under the replacing parabolic arc. We just replaced the portion of this curve as the arc of this parabola, and the area, this area dA A2 P2 D is approximately equal to the area under the approximating parabolic curve between these ordinates. Area of this area under this parabolic arc is by applying the parabolic rule, we get the area as 1 by 3 h by 3 into y1 plus 4 y2 plus y3. Hence, if A1 is the area, this is if we name this area as A1, we get A1 is equal to this area under the parabolic area under the approximating parabola, which is approximately equal to the actual area. Similarly, we apply the parabolic rule for the area joining the ends of the ordinates y3, y4 and y3, y4 and y6 and so on. We denote A2, A3 etc. An as the successive areas. We get A2 as A2 is equal to h by 3 into y3 plus 4 y4 plus y5. And A3 is equal to h by 3 into y5 plus 4 y6 plus y7 and so on. In general, An as An is equal to h by 3 into y2n plus 1 plus 4 times y2n, sorry here y2n minus 1 plus 4 times y2n plus y2n plus 1. Hence, the total area under the curve is A1 plus A2 plus etc. plus An is equal to h by 3 is common, h by 3 into y1 plus 4 y2 plus y3 plus here y3 plus 4 y4 plus y5 plus y5 plus 4 y6 plus y7 plus etc. plus the last is y2n minus 1 plus 4 times y2n plus y2n plus 1. H by 3 is common. The total area is equal to this, which is approximately equal, but the actual area of the region is area of the region A, B, C, D, that is integral from A to B y dx, where OA is equal to, this distance is taken as small a, and OB is taken as small b. Therefore, the total area from A to B is integral from A to B y dx is equal to h by 3 into here y 1 and y 2 n plus 1 y 1 plus y 2 n plus 1 plus 4 times y 2 plus here y 4 plus etc. plus 2 times the remaining ordinates, that is y 3 plus y 3, y 5 plus y 5, etc. That is 2 times y 3 plus y 5 plus y 7 plus etc., which is equal to h by 3 into the sum of the first and last ordinates, which is denoted as a, plus 4 times the sum of the ordinates y 2, y 4, etc. That is the subscripts are even numbers, that is 4 times b. We denote the sum as b, and plus here 2 c, where c is the sum of the ordinates y 3, y 5, y 7, etc. That is the subscripts are 3, 5, 7, etc. This is the Simpson's rule, geometrical interpretation of Simpson's rule. That is, we approximate the curve by a parabolic arc, and we find the corresponding area and sum all these areas, we get the Simpson's rule. Simpson's one-third rule approximates the area of two adjacent strips by the area under a quadratic parabola. This rule has been obtained by adding the strips in pairs. We have to divide the figure into an even number of equal strips, so that there will be an odd number of ordinates for the division. The smaller h, that is the width of interval, if the width of interval is very small, the approximation will be very closer. And Simpson's one-third rule on numerical integration is called a closed formula, because the endpoint ordinates also enter the formula. Now, let me conclude this session. In this session, we discussed Simpson's rule of integration. There are two types of Simpson's rule. First one is Simpson's one-third rule, and the second is Simpson's 3/8 rule. Thank you for listening this session. Have a nice day.